weighted averages when certain measurements matter more than others. So we run into this issue of I run a lab experiment and I get through my entire error propagation analysis, I get a final value with a final deviation of my error, some uncertainty to it, and I'm like, that's it, I have found it. And because I am the greatest, I am the number one, I am the alpha, I will say that my measurement, and we'll call this person A, my measurement is some value plus or minus, and before we used the symbol del to represent a deviation, so I could call this like the deviation of A. We're going to transition that to the standard deviation of A, taking a slightly more statistical approach on this with Gaussian distributions. Really, we can use these pretty much interchangeably, but just for sake of convention and how we've always talked about weighted averages, we're just going to use the sigma here. So the measurement I've taken, it's the measurement mine, it's measurement A, plus or minus the deviation of A. That's great. I'm a great person. I did my error prop, I feel great. But then a different Coach Botzer comes along. Maybe this is Brundon, maybe it's Brendan, who knows? And they take a measurement. The measurement they take has a value, plus or minus some different deviation. Maybe they took the measurement in a slightly different way than I did. Their measurement method is still valid, but they have more advanced and sophisticated equipment. So maybe their deviation is a little bit better than mine. Maybe it's a little bit smaller. If we would like to take all of the scientific data and put it together and say, like, as science, as a scientific community, this is what we believe the answer is. And, you know, if our scientific community is only 2 people, we can do this. But if our scientific community gets larger, if we have more and more and more people, well, we need to consider everybody's contribution here and see where our data takes us. Now, even though we're going to consider everybody's contribution, that doesn't mean every contribution means as much as another. If someone takes a very, very sophisticated, very, very precise measurement, the best that's ever been taken, then their data is going to have more weight to it. It's gonna carry more emphasis on what we believe the final solution should be. Whereas, you know, something that was taken a few hundred years ago with a stick, it's still good, but it's not worth as much. We're not going to consider it as much as something else. Okay, so these uncertainties here are really going to be how we determine who has the most pull in terms of what is the right answer. Okay, but we do consider all of the values here, assuming that the methodology to obtain them was correct. The way we do this, the way we take this weighted average, technically we start off with a Gaussian distribution, where we look at distribution functions and the probabilities of them, and we take chi-squared values into an exponential curve with the standard deviation weights. But that's the whole deviation of it. We simply right now don't need to worry about the derivation. Let's just worry about, if I have values, how can I use them? Let's get to the use it so that we can do physics. Not the math is very interesting, and if we're concerned about it, let's look that up on some other time. Okay? What we can do to find the new scientific true value of whatever we're looking for, what we claim to be the new accepted value, is we need to find what we're going to call the weighted average. Okay? So this is the weighted average, WAV. To find this weighted average, so this is what the entire community would say, hey, this is our answer, this is what we like. What we do is we take the summation or the addition of all of the weights that we have, so all of the weights of every single party's measurement, so group A, group B, group C, group D, all the way down the line. We take all their weights and multiply it by their individual values. So these up here, these are the X values. Those are the actual measurements there, okay? And we do this for every value, going from I, from the beginning, all the way to the end. And we multiply them and then add them all up. And then we divide that by the summation, or the addition, of all of the weights added together. So that's how we find a weighted average. The only issue with this is, this is pretty straightforward. We multiply a bunch of things together, then we add them, then we divide them by the addition of many weights. What are these weights? How do we find those weight values? Well, that's pretty straightforward as well. An individual weight is given by 1 over the deviation squared of that measurement. And these deviations are just up there. So we just pull these deviations down, we square them, we throw them in the denominator. That gives us the weight. With these weights, we can put them into this equation over here. Okay? So that's all we do. We find the weights based off of the deviations, and then we find the measurements from what we had. That gives us a weighted average. So this would be what the scientific community now thinks is the true answer. But what is the error on that answer? Each of these measurements up top had some error with them. They weren't 100% certain. They were good, and some better than others, but it's not a definite, this is the number, that's all there is to it. It's just, here's a number with an error. So we have the weighted average. What's the error on the weighted average? Well, the way we can get the error on the weighted average is we can say that, say that the deviation of the weighted average is equal to 1 over the square root of the summation of all of the weights. So what we would do is we'd find all of our weights just like we would up here, just like normal. We'd take all those weights, we'd add them all together, just like we did previously for the measurement value weighted average. But then we'd take the square root of that, and we'd say 1 divided by that value is going to give us the deviation of it. So what we can do with that deviation then is we could take these two values, and that will be the new accepted scientific value for this. This would be something like, hey, our measurement that we believe now is the weighted average plus or minus the deviation of the weighted average. And what this allows to happen is, because these weights exist and they're 1 over the deviation squared, as we have values with larger and larger uncertainties, the weights of those values, of those measurements, become less and less. So whenever we multiply them and trying to combine them into the actual true measurement, those values that are uncertain get less and less pull. They get less and less ability to say, my correct answer is the most correct. Because it's not. You have more uncertainty there. You're not really sure. Whereas values that have a very, very small deviation, well, a smaller value squared, that's going to be less. So they gain more weight, and then their values are going to shift towards the measurements with less uncertainty to them. So that's how we can take a weighted average. It allows us to take a lot of people's data and put it together just through these equations right here, based off of some values that you took before, and that would give us a weighted measurement and the measurement's deviation in a weighted format. So that's how you can take an entire class set, put it into one value. It's how you can take an entire world's or entire scientific community's data set and start combining them together. Okay, so that's a pretty neat thing there. If you're more interested in how did we derive any of that, we didn't do it in this video. There is some Gaussian probabilities that you have to start working through. That's a little bit more complicated than I want to get into here, but this is what we need to use. This is the big thing. This is how we can take a weighted average and put all of our values together. Okay, so with that, we're finished here. And with this weighted average and the error propagation videos that came before this for functions, powers, multiplication and division, and addition and subtraction, if you've watched all 4 of those and then you've taken a look at this here, that is all the error propagation and weighted average statistics that we need for the AP Physics 2 class just to get good at labs for college. We don't actually need this material for the AP2 test, but it is very helpful to use. It will get you through 95% of the stuff you ever need to get to until you start doing some high-level doctorate work, and then why are you coming to me? So definitely check it out if you haven't, some of those older videos. Hopefully it helps you out. If you've got any questions, just shoot them into the chat and let me know. Okay? Hey, take it easy. Have a good one, everybody. See you again.